Now, one of the tasks you're going to be faced with this unit is being able to identify the different types of intermolecular forces that exist in certain species. So I thought I'd make a video just going over some of these practice problems so you can get an idea of how it's done. This is going to require you knowing more than just what the intermolecular forces are. You're going to have to know about the structure of the molecules as well. So this would be a good chance to go back, review your VESPR, and which VESPR shapes have polar or non-polar shapes. Okay, so the first one is PF3. So the question for all of these is just going to be what intermolecular forces exist within this species. And so when we talk about this, I'm not talking about a single PF3, I'm talking about a beaker full of PF3, so tons of them. And what intermolecular forces are going to exist between two or more of those PF3 molecules in there. So looking at the shape then of this structure, if we would draw out its Lewis structure, it would have this shape right here, which we're going to recognize then as trigonal pyramidal. So we've got the electrons up there, and so it's going to make kind of that pyramid shape, which is going to be a polar species. So the electrons are going to get pulled towards one side, generating dipoles. And so if it's got dipoles, that means it's going to have intermolecular forces of dipole-dipole. But not only that, it's going to have London dispersion forces because all molecules experience London dispersion forces. Just as time goes on, those electrons are going to be redistributed around that molecule. It's going to induce dipoles and other PF3s that are around it. Next is NaCl. Hey, that's a metal and a nonmetal, so we should recognize that as an ionic compound. Ionic compounds are going to have the strongest of intermolecular forces, which is the ion-ion intermolecular force. What else are they going to have? Yeah, London dispersion forces, because all molecules have London dispersion forces. Next is CS2. We've got to look at the structure of this guy as well, and so it's going to be carbon double bonded to sulfur on either side. There's going to be lone pairs on the sulfurs, but those aren't necessarily going to make a difference. And so in this case, we're going to have a linear structure, which means the electrons are being pulled evenly on both sides, and so we're going to, as a result, have no dipole here. And so if there's no dipoles, that means no dipole-induced dipole, so it's only going to be London dispersion forces in action with carbon disulfide. And then finally, the methyl chloride. So we're going to have carbon bonded to 3 hydrogens, and that's going to be bonded to a chlorine. And so right here, it's going to have a tetrahedral shape, but it is not a symmetrical tetrahedral shape. And chlorine, which is going to be the most electronegative, is going to pull the electrons towards it. And so we're going to wind up with that uneven distribution, so a dipole negative over on this side, and a lower electron density, so dipole negative over there. As a result, we would have dipole-dipole forces, and we would also, of course, have London dispersion forces. So this methyl chloride is going to have the same intermolecular forces like the PF3 will. So this is step 1. Being able to do this is going to be important for the next videos, which is going to go over how to distinguish what elements have a higher boiling point or a higher melting point. And in order to do that, you have to be able to identify what intermolecular forces that molecule has at play.